Hey, AP Chemisters, this is Mrs. Vanderwall again. Sorry about that. I lost this page on my smart notebook and had to find it again. So here we have part two, which is going to finish up section 11.4. So we are talking about ionic solutions, and we're talking about if the ionic compound has several different ions in there, it will affect the vapor pressure. And let's think about it. Why does ionic compounds and covalent non-volatile solutes affect this vapor pressure? Well, consider this, that the ions have a positive and negative charge, and then the water molecules with their polar ends will be attracted to these positive and negative ions. Because of this attraction, the liquid molecules are held more tightly into the liquid phase, and fewer of them will be released into the gas phase. So that is why ionic compounds and those polar compounds, those polar non-volatile compounds, the solutes, will affect the vapor pressure. So here's a problem. If solution is said to contain a non-volatile solute, how does it affect the vapor pressure? Use the diagram below to explain. Why don't you pause this recording, write down your thoughts, and then turn the recording back on. Okay, welcome back. So the beaker on the left is a pure beaker, pure solute, and the one on the right has a solute in it. So notice what's going on. The beaker on the left looks like 8 molecules of solvent in the beaker as a gas, and the beaker on the right has only 5. So there's fewer molecules in the gas phase, therefore the vapor pressure has decreased. Okay? Let's continue going down here. So here we go. Glycerin is a non-volatile non-electrolyte, which means it doesn't break up into ions, with a density of 1.26 grams per milliliter at 25 degrees Celsius. Calculate the vapor pressure at 25 degrees of a solution prepared by adding 50 mils of glycerin to 500 mils of water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr, and its density is 1 gram per milliliter. So what are they asking you to do? They're asking you to calculate vapor pressure. So obviously we have a new vapor pressure. We are adding a solute into a solvent, and therefore we need to be using Raoult's law again. So let me write this down on the board. I'll be right back. Sorry. Okay, so that's Raoult's law, and then let's see what we have. What do we know here? They gave us the vapor pressure of pure water as 23.8 torr. So we can put that number in right now. All right, so now the next problem is, how do we find the mole fraction for the solvent? Well, obviously I need to find moles of the solute and the solvent. So I can do that. Well, to find moles I need grams. Grams, well, they didn't give that to me. I have mils. So how am I supposed to do that? Well, fortunately they gave us density and we can calculate. So why don't you pause this and then work this out, finding chi, the mole fraction, and then the answer should appear before your screen. Okay, so hopefully you had the opportunity to find the mole fraction for this problem. So the mole fraction is the moles of solvent over the moles of solvent plus the moles of solute. Well, now I had to find moles. So I was given volume of water. I had to use the density and the molar mass to find the moles of water is 27.75. I had to find the moles of glycerin, which they gave me 50 mils. The density is 1.26 grams over 1 mil. And then they had to give me the molar mass, which was 92.11, and divide to get 0.683 moles. So the mole fraction of the solvent would be the moles of the solvent over the moles of both the solvent and solute, and I got 0.975. Notice a couple things about mole fraction. The unit moles do cancel out, so the mole fraction is unitless. And notice that the mole fraction must be less than 1. If you get a number more than 1, you have made a mistake, so go back and try to find that. So now I have found the mole fraction of solvent. So here I need to then multiply that by the pure solvents thing, the 23.8 torr, and then we'll get an answer. So hang on a second and I'll put it up. Okay, so here is the final solution. So I took the vapor pressure of the solution as the mole fraction of the solvent times the pressure of the pure solvent. Here's the mole fraction number I gave you, 0.975. I put that here. Here's the original pure solvent, vapor pressure at 23.8 torr, and you multiply them together, you get 23.2 torr. Notice that the number is lower than the original, which it should be, because once again, that the glycerin, being a polar substance, we know it's polar because it dissolves in water, is attracting some of the water molecules instead of allowing them to vaporize. So we have fewer molecules in the beaker, fewer gas molecules in the beaker, therefore the vapor pressure went down. Okay, so here's problem 13. Why don't you go ahead and pause this and work it out, and I will do the same, and we'll come back and you can see how you did. Okay, so here is the completed solution to this, solution to this problem number 13. So using Raoult's law, once again, we have the vapor pressure of the solution equals the mole fraction of the solvent times the vapor pressure of the pure solvent. Over on the right, I found how to calculate moles of water and moles of the solute. Excuse me, I plugged them into my equation for mole fraction, and I got my mole fraction is 0.929. Once again, this number is less than 1, which is a good thing, and there is no units. So plugging this into Raoult's law, we have P of the solution, here's my mole fraction, here is my vapor pressure of the pure solution, so here is my final answer. Hopefully you did that right. Okay, let's see what happens next. Now, we do not always use a solute that is non-volatile. Sometimes we actually put another liquid in that also evaporates easily. So now we have two liquids that both vaporize. So we should expect that there will be some of the solutes vapor present and some of the solvents vapor present. So we have a combination of both. So checking this out, obviously we're going to have to use Raoult's law, but we're going to have a variation of it. So again, it says non-ideal solutions, liquid-liquid solutions in which both components are volatile. So we actually have to find the mole fraction of the first one. A can be the solute or the solvent, and B is the other liquid. So they say the partial pressure with a little zero top that you call an aught, the naught there. P naught is the vapor pressure of the pure solvent, and then the PA and PB are the partial pressures of each. So the ideal solutions does obey Raoult's law, and as all things in life, nothing is perfectly ideal, but some things are rather close. So we can actually look at these deviations from Raoult's law, which means the negative ones, they are lower than predicted, and the positive ones, they're higher than predicted. Now, what causes something to be lower than the predicted value? Well, if you have a lower deviation, that means you have fewer gas molecules in the container. Why would you have fewer gas molecules? Well, because the solute and the solvent are very, very attracted to one another, and they will stay in that liquid phase, having fewer gas molecules in the gas phase. So that would be a negative deviation. A positive deviation is, again, there's only weak attractions, so more are likely to enter the gas phase, and so you have a higher vapor pressure than expected. So these three graphs are showing that. So notice on my notes, they're colored. Yours is just black and white, sorry. That the red, let's call this A, and the blue, let's call it B. So what is happening here, as the mole fraction of A increases, the partial pressure of A will also increase. Well, if one goes up, the other one has to go down. So as A increases, B will decrease, and you're going to be adding these two numbers together, and that's what the black line is showing, that is the sum of the partial pressure of A and the partial pressure of B. So this straight line right here would be the ideal solution. It'd be acting just like Raoult's law would predict. However, in reality, notice that sometimes the expected value is actually less than that Raoult's law would predict. Why? Because the solute and solvent are highly attracted, meaning fewer molecules are in the gas phase. And over here, notice that these are bowed out so that they have higher vapor pressure than what is expected. That's because they have weaker intermolecular attraction. So if they're weaker, that means more particles will escape into that vapor phase. Okay, problem number 14 is dealing with such a situation where you have both volatile solute and solvent. Both want to become a gas. So we have acetone and chloroform in this situation here. Notice not water. Water does not really vaporize all that easily when compared to these others. So we have a solution is a total vapor pressure of 260. So that's what it really has. So now we're going to use Raoult's law to see what it should be according to him and compare it. Is this 260 higher than what we get? Is it lower than what we expect, or is it exactly what we're supposed to get? So let's check this out. Here we have the vapor pressures of pure acetone and pure chloroform. Those are your P naughts. And let's go ahead and do the math. So you go ahead, solve for mole fraction of acetone and chloroform, and let's see at least how we get there. Okay, here is this problem worked out. The first thing I found were the moles of acetone and the moles of chloroform. They made the math really easy for you. I hope you noticed that. So you got 0.100 moles using correct sig figs for each. Therefore, the mole fraction over here is actually 0.500 for each of them. It's the same. You have equal amount of moles, so the mole fraction is 50-50 basically. So here is the Raoult's law for the non-ideal case, basically where both you have volatile liquids for both, so you have to put the chi, or the mole fraction for A, times the pure solvent vapor pressure, and then do the same thing for B. So I plugged in the numbers, 0.5 times 345, excuse me, and 0.5 times 293, and we add it all together, you should get 319 torr, hopefully. And compare this number than what they got up here. Up here is your 260. That's the experimental value. That's what it should be, or sorry, that's what it's measured to be. And compare it to the 319. It's less than that. So it's a negative deviation. So why is it a negative deviation? Why is it smaller than Raoult would predict? Because there's stronger attraction between the molecules. I just want to point out a little bit from this problem compared to the problem before. We were talking about for 25 degrees Celsius, the water had a vapor pressure of 23 torr. Notice that water's vapor pressure is much, much lower than both acetone and chloroform, and that's because of the much, much stronger intermolecular attractions that hydrogen bonding has. All right, so this concludes our lesson on section 11.4. There will be problems to follow, so check your texts and your notifications to see which practice problems you ought to be doing. I hope this helps, and of course, if you have any questions, jot them down, and when we come back to class, be sure to ask them. Have a great night. Bye-bye.